you for joining today's class. Everyone is ready? Shall we start? Okay, today's topic for discussion is functions. But let me go to our last class discussions and make some comments there, make some conclusions, and we will come back to this. So what we have, so what we did last time. So we had two sets, two non-empty sets. One of them is A, another one is B. Then any subset of this cross product R gives us relation on this set A cross B, or from A to B. So you may have three sets. R as a subset of A cross B cross C, say. Then you may have n sets. A1 cross A2 cross etc. AN. So each this kind of relation has its domain. So let me first what we have. We have domain of R. I will remind you what is that. So this is those elements of A. I start to use X. A such that there exists Y from B with the following property. X, R, Y. Or it is the same. This pair X and Y is an element of R. An element of R. We have image of this relation R. Of course, this is subset of A. Now I am talking on the first case when we have A cross B. So the image is those elements of B such that there exists X from A with the property X, R, Y, or it is the same, this X, Y. Here X, Y is the element of R. This is subset of B. Number 3, we have graph of R. This is a shape. Shape of R in a Cartesian plane in A cross B. See. Number 2, what we have. Last time we considered the case when A is B. So that means we have R subset of A to the 2. In the first case, the second case, we have R as a subset of A cube, and R is a subset of A to the N. Look at this. If A is R, in this case, you have single variable calculus. If R is subset of A cube, then you will get two variable calculus. So I'm fixing this. A is R, these three cases. In this case, you have two variable calculus. In this case, you have multivariable calculus. More precisely, you have n minus one variable calculus. Multivariable. Okay. Now, we identified three properties of such kind relation. So in this case, you have binary relation. In this case, it's ternary relation. This is ternary relation. In this case, you have n-ary relation. So now I will focus only binary relation case. So it is R is a binary relation on set A. Now we identified three properties. So first property is reflexivity. Reflexivity means for any x from A, x, R, x. The second property is symmetricity. That is, if x related y is related to y, then this implies y also is related to x. And the number 3, transitivity. Transitivity means if you have x related y and at the same time y related z is related z, then this implies x is related to z. So these three properties we identified. You can identify more properties, but we will deal with only these three. So that's why I will just stop on these three properties. Those relations having these properties are called equivalent relations. The R in this case is called equivalent relation. Equivalent relation. Okay. Now, one observation from the first one. The first one guarantees, this one guarantees that domain of your relation and the image also range of your relation R is A. If you have a relation having this property reflexivity, then its domain and the range is that set itself A. The symmetricity last time we already discussed. Symmetricity means shape of the graph is symmetric with respect to diagonal. Okay. Now, hello. Anyone ask question or what? Please me. Oh, that one is attendance. Okay, so let me now share my slides. So I want to go through examples which we had last time and give some comments on that examples with respect to these properties. So first example was that equality relation is equal to. So let's discuss all the things on that particular case. Equals. How about domain? Domain is R. Why? No, you can just first take verify these three properties. You can easily see equal relation is reflexive, symmetric, and the transitive. So this is equivalent relation. Since it is reflexive, according to this property, domain and the range of that is A itself. No choice. So domain is given as a R in that slide. You can see. Range also is R. I'm just limit myself to R. A is R case. Putting there. So properties already I mentioned, because if no, the easy for reflexivity, symmetricity, and transitivity to check. Okay. So now, how about graph? No graph. You can draw a graph of this. Number 4. So now RA is R, and my relation is equality relation. So that according to that discussion, we have domain, range, then this one is equivalent relation. This is an equivalent relation. Okay? So what is the rest is to draw a graph. Graph of this diagonal. Diagonal in this graph. This is the graph of R. Because according to this relation, x or x must be y. All those points from xy plane, this diagonal, they are elements of R. The graph is just diagonal. Next example is that example was. Any question regarding this example, please? Is less than. Next example. So we'll again go through all this with respect to that is less. So what do we have? Just let me erase some part.
Ni letak dalam beg dulu. Ni lain kali Mak nak pesan, walaupun baju tu kotor, lipat dia elok, jangan main masuk.
Any question, please?
Elok sikit rupanya.
Okay, number 5. So now A is R, and my relation is less than. Is less than. I check for domain of R. Domain of R is R.
Exactly, press RA. Simpan sekarang.
Domain is R. The image also is R. How to prove it? Because we know this inclusion. Domain is a subset of R. Now we need to take any R and show that R is in the domain of relation R. So I will take any R from R.
Ada lagi satu biru.
Then
Warna gantung kan?
I prove that there exists S from R such that R is less than that S. So clearly I will take as a S R plus 1, see. It's a S. If I take R plus 1, then R will be less than R plus 1. So that means I have this inclusion. The same this inclusion, because I have this inclusion, I want to prove the converse. For this, I will take R. I will take this time S from R, and there exists R from R such that R is less than S. So this time S I have, I should find R. So for this R, I will take S minus 1. Because S is given, just subtract minus 1. You can put any number here. It will be less than S. So that's why I will get this inclusion. Thus, I have equality. All right. Now, that properties, it is definitely is not reflexive because A is not. Why? Because you cannot say X less than X. Cannot be. So reflexivity doesn't hold. Symmetricity also doesn't hold. Why? Because if X less than Y, Y is not X. Because already given that X is less than Y. So no transitivity. How about no symmetricity? Sorry, but transitivity holds because if x less than y, and at the same time y also less than z, then this implies x less than z. So that's why transitivity holds. Okay, so how about graph now? Let us draw the graph of this relation. Just coordinate plane. I have diagonal. And all points over this diagonal, not including diagonal. This is a graph of R. Without this diagonal, all points over that diagonal is a graph of this relation. Because for all points over that diagonal, we can find x. Any of this point is more than x. So that's why this part, zebra part is a graph. Is it clear or not?
X greater than y, then the graph is below.
If x more than y. If x more than y, then you will get below of the diagonal, but not including the diagonal. So we will see in next example. If x more than y, go to next example. If x more than y, then you will get below of the diagonal, but not including the diagonal. So we will see in next example. X more than y. Go to next example. More than y, then
less or
you will
equal.
get below
That's also
of the diagonal, but not including.
Let me just.
So we will see in next example. X more than y.
Or
Go to next example. More than y, then
less or
you will
equal.
get below
That's also
of the diagonal, but
all
not
this,
including.
Let me just.
So we will see in next example. X more than y.
graph.
Go to next example. More than y, then
less or
you will
equal.
get below
That's also
of
right.
the
It's
diagonal,
better
but
to-
yes. Fix here. Yeah, fix this also. So now, number 6. Number 6, A is R again. Then my relation is less or equal. Again, you can see domain is R, and the same range also is R. Properties now, but this has E because of this equality. Equality is there, so that's why x less or equal to x itself. So that's why reflexivity holds. Symmetricity doesn't hold. Transitivity holds. So this is properties. So you can see it's not equivalent relation. So now graph, GR. Small difference here. For this case, you should include the diagonal. Together with diagonal is part of the Cartesian plane. This is GR. This is a is equal or is less than or equal case. Okay, now not equal case. Again, domain is R, clearly can be seen. So domain is R, the range is R. Now, no reflexive, no A, because element cannot be equal to itself. Cannot be non-equal to itself, sorry. A doesn't hold. How about the B? B is a symmetricity. If A is X is not Y, then Y also is not X, right? So symmetricity holds. How about transitivity? Transitivity doesn't hold. Why? Because you can see 2, last time we have seen it. Last time we already discussed it. 2 is not equal to 5. So at the same time, 5 also is not equal to 2. But you cannot conclude 2 is not equal to 2. This is wrong. So that's why transitivity doesn't hold. Transitivity doesn't hold. So now, graph. Graph very interesting. Now, you should remove from the plane only this diagonal. So graph is, as I will correct this, you should remove only this diagonal. Let me write like this. You should remove this part, cut out. All beyond of the diagonal gives you a graph of non-equality. R is not equal relations graph. Okay. Next one. If any question, please stop me and start to ask questions. This is an example which also last time we discussed. A consists of 8 elements. A1, A2, etc. A8. But each element is set again. So these all finite sets. Finite number elements set. A1 is ABC, A2 is 1, 2, 3, A3 is empty R, A4 is 1, 2, 3, 4, 5, A5 is natural numbers, integers, E, F, G, A6 is A1, A2, A3, A4, A5, A6, and A6 is, oh sorry, just remove this. A7 is empty and 8 is 2 and the Q. So please ignore this because repeat it. Now, the relation is the same, has the same number of elements S. What we have? Domain of R is A. The range also is A. This comes from these properties. It is reflexive because you can just write all relations between this set. So A1, A2, A4, A5, A3, A8, and AI, AI. So this means AI, AI means reflexivity. Since it is reflexive, domain is A. And the same range also is A. Now, others you can see here. Asymmetricity also holds. Why? Because if you have say one set A, or cannot use A, right? Let me take set X. Cardinality of this set is Y. If they are equal, X and Y, cardinality of X and Y equal, then of course the cardinality of Y also is X. That is a symmetricity. This means X are X, X are Y. This implies Y are X. This one is symmetricity. About transitivity, we have X, Y R, and Y R Z. Then, can we say X R Z or not? Can. Why? Because this is the same to say X is Y, and this means Y also is the cardinality of Y is the cardinality of Z. From these two, you can conclude that the cardinality of X is the cardinality of Z, which is the same X RZ. So transitivity also holds. So that means this relation is equivalent relation on A. Equivalent relation on A. How about graph? So now you can draw graph. We have 1, 2, 3, 4, 5, 7, 6, 7, 8. Here also 1, 2, 3, 4, 5, 6, 7. Last one here, 8. Diagonally is there. All diagonal points are there. All diagonal elements there. Why? Because AI are AI for I 1, 8. 1, 8. Then next one is 1, 2. 1 and 2. This point also in the graph. But symmetric point also is there. The next one is 4, 5. So 1, 2, 3, 4. This is a 4. 1, 2, 3, 4, 5. This point. Symmetric point also is there. Then next one is 3, 8. 1, 2, 3. And the last one. This. And 8, 3 also is there. 1, 2, 3. So this is a graph of your relation. These dots. This is a graph of your relation R in this particular case. Okay? All right. Next example. Next example is, again, A is R, but relation is given by some formula now. Relation between X and Y is given by this equation. By this equation, Y minus cosine X. Y minus cosine X. Let me. You have A, R, and your relation R is given, so X, Y, from R squared, relation is given as a Y minus cosine X is 0. Now, first of all, domain. Domain is R. Why domain is R? Because domain is R, right? Oh, correct. Because you can take R. We know this inclusion. Now I want to find another, prove another part. Why R is a subset of dr. I will take any R, prove that there exists S from R such that RS in R. Or it is the same to say S minus cosine R is 0, or S is cosine R. Because for any R, you can evaluate cosine of that. You have a cosine of any real number R. So the result of that evaluation gives you S. So this S is the value of cosine function and at point R. Okay, so now how about range? Image. The image is -1 and 1. Again, this is subset of this. This one is, this time I should do proof, right? I claim the image is -1 and 1. So what should I do? So I will take any S from -1, 1 and show that there exists S, or there exists R, from R, no problem. From R such that this pure RS is in R. So indeed, since S between -1 and 1, so I can solve this equation. Since mod S is no more than absolute value of X, S is no more than 1, so there exists solution to this equation. So that solution I will take as a R. So that R, where cosine R is S. Or if you write it, R is cosine -1. Cosine -1 of S. R cosine function. So you can see since the cosine function range is a -1 and 1. Okay, next one is graph. The graph now, by the way, it's interesting graph. Now you know cosine function graph, right? So this is 0. This one is pi over 2 minus. This one is pi over 2. Here you have pi, 3 pi over 2. Here minus 3 pi over 2. Oh, sorry, here minus pi. First a minus pi, then minus 3 pi over 2, right? See in there. So minus pi, this goes up, so it goes up. So this exactly cosine function graph. Okay. Next one is x minus y squared. Example. Domain of that is, let me write here again. A is R. Then R is given as xy, R squared. X minus y squared is 0. Domain first. Domain of R is, what's the domain? Those x where can y can be found. Of course, it is R, R plus positive part together with the origin. R plus 0. Then for the range, we have R. By the way, we haven't checked for this to be to have that 3 properties. Definitely you don't have reflexivity because x equals to cosine x only at 0. It must be for all points, but for only one point. So that the reflexivity doesn't hold. Symmetricity also doesn't hold. Transitivity also doesn't hold. For this, you don't have neither of them. Neither of the 3. Here, again, you can check. A doesn't hold. B also doesn't hold. And the transitivity also doesn't hold. No, because what does it mean, transitivity? Transitivity means x is y squared, and the y its tan is z squared, see. Then you can, from here you can see x is z to the 4, not 2. So that's why transitivity also doesn't hold. So it is none of these properties holds. Here, graph, you can see again graph of this. It's a graph of your R. That parabola, xy squared parabola. Why these two examples? Because we will discuss functions. Functions also functions are relations, but the particular case of the relation. Yeah. You have a graph. You can construct such a relation according to that graph. For any graph, you can create a relation. Because graph is given means you have some correspondence between that points in that two exist. So according to them, you will just, for each point, you will put that relation, just create who is related to whom, and then you will get. In a general way, if you have some graph, any graph, any shape in your Cartesian plane corresponds some relation. Any graph will define some relation there. Okay, so now why we specify, why we identified that properties. Why equivalent relation is better? It is much nicer than other relations. It is explained by the following proposition. If you have some equivalent relation on a set X, then equivalent classes, then you have these four properties for these equivalent classes. Each element has its own equivalent class. For any X, you have its equivalent class where X belongs to. The X belongs. Then you have equivalent classes if some element from some equivalent class of some element X, then equivalent class of the two elements are the same. If you have non-empty intersection, they also coincide. Then any element X belong to this S is extra, belong to exactly one equivalent class. One equivalent class. So this is a very nice property because it gives you the following partition. Now let us go to our examples. Two of them are equivalent relations. One of them is equality relation. Another one is that related to finite sets. So let us do the same by this the definition, how to split into subsets. The two sets. The first equivalent relation was equality. So we had A, R, then R was is equal to. Okay, let us find Cx. So I will take any x from A and find Cx. What does it mean, Cx? I should take all the elements of, let me take Let me write here R, since A is R. So I will take a real number, then all equivalent to that real number numbers I will include to this set. Which elements of R is equivalent to X? Which elements of R are equal to X? Only X itself. Nothing else. So now, equivalent class consists of only on X. Single point set. So that's what we have. R is written as union of this Cx. X runs my R. This is a partition. So these are partitions. Cx, index sets X run R. So each Cx is just singleton. This is the family of subsets. This family of subsets form a partition of R. This in that example, equality. Okay? Any question?
Examples?
Let me take another example of this. So I have A, which is A1, A2, A3, A4, A5, A6, A7, and A8. According to our definition of our R, we will get AI, R, AI. So I is 1, 2, 8. Then A1, R, A2. What was there? A3, right? A3, R, A5, right? Am I right? In that example. Okay. A1, A4, then A3, A4, A5, A3, A8. Right? Okay. Since A4, A5, A5 also A4 because symmetricity. A3, A8, A8, A3 also symmetry. Let me now find CA1. So I will take all that equivalent to A1. So first of all, it is A1 itself and A2. This is CA2. CA3. The first of all, this is A3 plus, I should add A8. This one is CA8. CA4 is A4 itself first, then A5. CA5. Oh, nothing else. I have the following partition, the following sets. The first member of partition is A1, A2. Another one, A3, A8. I missed one. 1, 2, 4, 3. Must be A1, A2, A3, A8. Oh yeah, correct. Let me find A6. I have another 2 elements to find class of current class of them. So this is just A6 and C A7. Also A7 only. Okay, so I have the following subsets. The following family of subsets. There, CA1. Let me write this as CA1, CA3, CA4, CA, CA6, and the CA7. This is a partition. Why? Because you can see intersection of them is empty. No any two intersect. Then union of them must be A. So let us see. A must be CA1 union CA3, CA4, CA6, then CA7. Indeed, this one is A1, A2. This is A3, A8. Next one, A4, A5. This one, A6 and A7. So intersection of them, CAI, CAJ is empty. If I is not J, first among them, then union of them is the set itself A. So that means this family of subsets is a partition. So any equivalent relation form a partition. And the converse also is true. If you have some partition of a set, then you can create equivalent relation to that partition. You wanted the number examples. Examples in numbers. Okay. Let me take, say, as a I will take 1, 2, -2, 3, and 5. All right. Now, equality relation. So 1 is equivalent to itself only. 2 equivalent to itself. Each of them equivalent to itself only, nothing else. So that's why you have how many equivalent classes? C1, C2, C-2, C3, and C5. They are disjoint, being one element subsets. If you take a union of them, it's exactly A. No, just now, like in this example. Okay? Now, the converse of this. Let's say you have some partition. Now, some partition of set A. So you have A is written as a union of AIs, AI intersection AJ is empty if I is not J. So I want to create some relation. Then prove that relation is equivalent relation. I will take element x, and element y. I will call this element x and y are related to each other by this relation R if x and y belong to one of these member of this partition AI for some I. Yeah. No. I will take any x and the y. If they are in the same member of this partition, I will call them equivalent. Yeah, each time I will choose one element. Okay, let me draw, in that case, some picture. This is a partition, right? This is A1, A2, A3, A4, A5, A6, and A7, C. According to this definition, all elements of this subset equal. All elements of this subset also equivalent to each other. All elements of this subset equivalent to each other, etc. So this definition gives you such a relation between the elements of A. So I prove that this R is equivalent relation. Why? Because if I take X and X is related to X or not? Of course, because X is sum of, because this is a partition. So that's why any X must be in some members of this family of subsets. So that's why X belongs AI for some I. There exists I, so that X belongs to AI. So that's why according to this I can write XX, but we don't write like this because X belongs to AI, and then another copy of X also belongs to AI. So that's why X related to X itself. This is a reflexivity. Now, symmetricity. If X are Y, that means both your elements X and Y they are in some AI because they are disjoint. So that's why it cannot be X to be in one and the Y cannot to be another one. So that means XY is in AI. According to that definition. Now, if XY in AI, so I can write YX also is in AI, right? But this means your Y related to X. So symmetricity holds. Transitivity now. If X are Y, and at the same time Y also are Z. What does it mean? This means X, Y is some AI. This means Y and the Z also in some IJ. But definitely your I must be J. Why? Because both of them, Y is in AI, and at the same time, Y also in AJ, but they are disjoint. cannot be for disjoint. If I is not J, so they are disjoint, intersection is empty, so cannot be element Y be in both sets. So from where I will get I is J. So I is J, just instead of this J, I should put I. Since XY in AI, YZ also in AI, so XZ also in AI. So that means X related Z. So that is a transitivity. So if you have some partition, then you can create some relation, which is an equivalent relation under this definition. So that means any equivalent relation gives some partition of your set, or if you have partition, then you can define equivalent relation according to that partition. That is very important property. We will see such a property how to use in our some examples. So this is that proposition which I just now demonstrated. Okay, now relations on Z, one relation on Z. That means congruence relation. Congruence relation is given as follows. If you fix some n, positive integer, then two element x and y from Z, you will call, and that relation related to this n, mod n, we will call congruence relation mod n, if their difference is divisible by n. Divisible by n. So that relation is given specific notation. Now our set A is Z. My set A is Z now. Changes. On Z, now I will define a relation on Z by the following rule. So I will take two elements. One is x, y, from Z, x, r, y, if and only if x minus y is divisible by n. So n is fixed. N is a positive integer. According to our notation, we can write n is some natural number. A natural number. Okay? So this relation has its own notation. It is because it is related to this positive integer n. So x congruence y mod n. So in this case, we call x is congruent with y mod n. It is easy to see. This is equivalent relation. Is an equivalent relation on Z. We should to verify that three properties. A, definitely X congruous with X mod N. Why? Because X minus X is 0. So 0, you can always write this up. 0 is 0 times N. B, last time we start to write it. So mod N. That means X minus Y is divisible by N. Q is an integer. Then from where I will get Y minus X, I will write it as minus Q. If Q is an integer, minus Q also is an integer. So that means Y X mod N. So this is a symmetricity. Transitivity now. If X Y mod N and Y Z mod N, so this means X minus Y is NQ1, Y minus Z is NQ2, add up, the result will be X minus Z is N times Q1 plus Q2. This is a Q. If Q1, Q2 are integers, then the sum of that integer also, of two integers also is an integer. So this is a Q, a Z, sorry. So from where I will get X congruent Z mod N. So this is equivalent relation. Okay, so now let us equivalent classes. See equivalent classes, try to find. According to that proposition, any element belongs some equivalent class. So I will start from 0. So I want to find equivalent class of 0. For the equivalent classes also, there is a special notation. So if I equivalent class of X, I will denote as X sub N, or sometimes just without this N if N is given. So that's why let me write a 0. All elements which are equivalent to 0. So that means those X from these such that X 0 mod N. So that means X minus 0 is divisible by N. So that means X must be a multiple of N. This set is denoted as NZ. All multiples of N. Let me take equivalent class of 1. So that means this is those X from Z such that X 1 mod N. It is the same to say those X from Z such that X minus 1 is divisible by N. It is the same. If you divide x by n, you will get remainder 1. So this you can write 1 plus nz formally. And so on. You can write until n minus 1. So n minus 1 will be n minus 1 plus nz. So what this means? These are numbers. Dividing by n, you will get remainder n minus 1. Because you have division algorithm in Q, in Z. A and B, you have A and B. You can write A as a BQ plus R, where your R is 0. Let me write N here, N Q, R 0 and N. This R may be 0, 1, 2, 3, and until n minus 1, according to here. In this case, R is 0. In this case, R is 1. Next case is R is 2, etc. Then last case, R, this one is your R. Those numbers dividing by n give remainder R. So how about n? Now, of course, n, what is this? This means those x from Z such that x n mod n, or it is the same to say those x from Z such that x minus n is divisible by n q from Z, or this x is n times q plus 1 q from Z. Again, you will get some multiple of n. You already multiples of n, you counted here. So that's why this case is 0. This case is 1. Oh, sorry, this case is 1. Next one. This one is n plus 1. N plus 1, etc. This case is 2. N plus 1, 2n, 2n minus 1. So you will get next is 2n. Again, you will get 2n, this subset. Is 2n, 2n plus 1, 2n plus 2, etc. This one is 3n plus 1. Next one is 3n, 3n plus 1, etc., etc. So result, what you will get result? Because we know these are this is family of partitions. Partition of Z. According to this discussion, only you have from 0 until n minus 1. No more. Because if you go beyond, then you will repeat again. For n, you will get this. For n plus 1, you will get this, etc. For n minus 1, 2n minus 1, you will get this. Then for 2n again, this, etc. You will repeat. So, all together, you have only n equivalent classes. Or let me write that equivalent classes. 0, 1, minus 1. Your Z is written as 0, 1, and minus 1. This is a partition of Z. Partition of Z. Okay, but this set has one remarkable property. There is addition and multiplication operation there. You can add any two elements of Z, the multiply. That addition and multiplication operation can be just induced to this set of partitions, set of equivalent classes. So how to do it? So I have two equivalent classes. One is A, and one is B. I will define addition operation between them. So addition operation is what I will do. First, I will add them. This addition in Z, add them, then divide them by N, and see the remainder. So what is the remainder? I will put here that equivalent class. Another operation is multiplication operation. Again, what I will do, I will multiply them, multiplication in Z, and the result I will divide by N with the remainder. What remainder is? From this list of classes of equivalent classes, I will put here. N is 6 case is given here. Again, I came to that point in my last class. Never mind. So I have this is addition and multiplication operation, well defined. This is table of multiplication for addition for 6, N is 6 case. And the table of multiplication for, sorry. This is multiplication table. And the previous slide is addition table. Addition and multiplication. N is 6 case. The two tables are given. I have to stop here because time is over. And thank you for your patience. Then I hope next class I will start again. I will start from functions straight away. Any questions, please? From audience? From Tashkent, Samarkand, please? Any questions there? Hello, are you there? Hello?
No questions.
Okay, thank you. See you.
Thank you.
Thursday. Thank you.
Thank you.
Bye-bye.